Great. Yeah, thank you, Dominic. Yeah, so first I would like to thank the organizer for organizing such a wonderful workshop in this beautiful place. Today I will talk about the theory of joint phonomagnetic moment in Dirac semimetal. The problem we have been working on for last 2 years. Okay, before introducing our result, let's first acknowledge the collaborator. So this project is mainly driven by a very talented student, Wenqing. We also collaborate with many postdocs in the group between me and also between Professor Chiral at the University of Washington. So I will give a brief introduction to the phonomagnetic moment, in general, and I will present our theory based on the gauge theory for phonomagnetic moment in Dirac semimetals. So there are two aspects of our theory. One is based on the gauge theory. The other is about the geometric origin of the phonomagnetic moment. I think I don't need to talk much about it for this audience. So we know that in material we have ions. So if we drive ions by circular polarize, we can excite the circular motion of ion, and then in that way it can produce ion magnetic moment or phonomagnetic moment. And as we know, because ions are very heavy, right? So the induced magnetic moment is expected to be small, which is the order of nuclear Bohr magneton, which is about 2,000 times smaller than the electron Bohr magneton. Right? So this is a baseline for the problem. But however, and indeed, there's a calculation by our organizer, Dominic, and also Nicholas Brighting in this nice paper. Yeah, so in those ionic crystals, indeed, the predicted phonomagnetic moment are small, and is considered with a theoretical expectations that is in the order of nuclear magneton. And as nicely reviewed by Andre in his talk, and there is a recent experimental effort to measure phonomagnetic moment in real materials, and quite surprisingly, the observed magnetic moment is much bigger than one would naively expected for ion motion. Right? In this particular example, done by Peter Armitage's group, actually they found a huge magnetic moment associated with the phonons. And the magnitude is the order of electron Bohr magneton. Right? So it's a 2.7 electron Bohr magneton from the linear fitting of the splitting of the phonon frequencies. And there's another experiment also reviewed by Andre, and in this topological crystalline insulator, and they have also seen the phonomagnetic moment, which is the order of nuclear electron Bohr magneton, right? So this raises a serious question. So how can we get such huge phonomagnetic moment in those Dirac semimetals? And this motivates us to think, what is the underlying physics. In order to get a phonomagnetic moment of order of electron Bohr magneton, we must consider electrons, because only through electron phonon coupling we can get such large electron phonon phonomagnetic moment. So the question is, how does electron phonon coupling give rise to this large phonomagnetic moment? And before us, there's one nice theory done by Yafei and also Professor Chen Yu. And so in this theory, it's a adiabatic theory. So basically, they consider the motion of ion that drags the electron into motion, and in that way, you can produce a large effective phonomagnetic moment. And this can be simply understood as follows. So because the dynamics of the phonon is slow compared to electron dynamics, so we can treat the phonon motion adiabatically, and in that way, the electron wave function can be written in a so-called synthetic dimension. So kx, ky are the electron wave number, and the ux, uy are the phonon coordinate. Right? So in this 2D problem, then effectively we have become four-dimensional problem. So in this 4 dimension, we have a so-called monopole charge which can produce large barrier curvature. And in that way, they can induce large phonomagnetic moment due to the coupling between electron and phonons. And since this theory is based on the adiabatic approximation, so it breaks down if the gap closes. For example, this calculation. Right. So this is a calculation in this paper. So for the for the gap phase, so we have well-behaved results. But once the band gap closes, like in Dirac semimetal, actually you see a divergence in the phonomagnetic moment. This divergence is an artifact of the adiabatic approximation. So we need a new theory if we are considering semimetals or gapless system in general. So here we derive new theories based on some concept in high energy physics. So basically we can treat the phonon as an emergent gauge field or as a so-called frame field in Dirac semimetals, depending on their symmetry. And in our approach, we use the multi-scale modeling approach. Basically, we'll start from DFT toroid band structure, and we construct hard-band model, and also we'll use a quantum field theory and also symmetry consideration to give right physical picture. So here is a simple physical picture because we are considering Dirac semimetals, so we have Dirac cones, and we know Dirac cone are topologically protected objects, right? So you cannot remove Dirac cone easily by small perturbations. So if we excite phonon, then what phonon can do is one way phonon can do is to shift the position of their node, and once their node is shifted in momentum space, then we can regard this shift as an effective gauge field, right? So this is one way how phonon couple to electrons, and there's another way that electron can couple to phonon. That's through the renormalization of velocity. For example, we can compress the crystal, we can enhance the Dirac velocity, right? And this can also be regarded as a change of metric in the space. Right? So basically, the phonon can be either regarded as a gauge field or can be regarded as gravity in the Dirac semimetals. And so now the question is, under which condition phonon can be regarded as gauge field? And here is a simple criterion. So based on symmetry consideration, basically, the requirement is that the minimal coupling between the momentum of electron and the phonon field as a gauge field should be compatible with the little group at the Dirac node. And here is an example, how to understand this statement. So let's say, let's consider a graphene as a concrete example. And for graphene, we know that there are two Dirac cones at the k and minus k point, and the little group at the Dirac point is a threefold rotation along the z-axis, and also the composite operation of inversion and the time reversal, right? So for momentum, right, it's even under the inversion and the time reversal operation. So that means in order to regard the phonon field as a gauge field, it must also be even under this operation. And one can construct the even even field as that is given by this expression, which has been known before for the acoustic phonons. But this can also be applied to optic phonons. And here you see, if you look at the expression carefully, for the gauge field it's a vector, but for the string it's a tensor, right? So tensor is a rank 2 object. So how can tensor to be equal to a vector? And this is because we have C3Z rotation symmetry. Basically, the angular momentum is conserved up to 3. Okay, so for the tensor field, it has angular momentum equal to -2, and for a vector, it has angular momentum equal to 1. So 1 equals -2 because of C3Z rotation symmetry. And we can also construct an emergent gauge field for the optic phonon. And for optic phonon, we can write down this expression between AX is proportional to the uy. Uy is a displacement field. And because, in graphene, we have two sublattices, right? So this uy is actually even under inversion, because under inversion, we swap A and B sublattices, right? And also we change the coordinate, change the sign of the coordinate. So then U is even object under inversion. And when we write the gauge field in that way, actually this is compatible with a little group at the K point. So this is the result we can write down. It's not responsive. Okay. So basically, yeah. So we have a momentum coupled to the phonon field, and that work as an emergent gauge field. As this is for the optical phonon. And of course, here we use a symmetry argument to write down the phonon. Is the coupling between phonon field and the electron. And actually, you can do more systematic derivation based on Taylor-Binding model. Basically, if you distort the lattice, it modifies the hopping, and you can run this machinery, and you can reach the same conclusion. And here we also did some derivative calculation for graphene. For graphene, we have 6 phonon mode. And let's consider the optical mode here, right? And now if we excite this optical phonon mode, it will shift the position of the Dirac cone as shown here. But this this is without the optical without the phonon field excitation, so the Dirac cone is at the K point. But if we excite the optical phonon, actually we can see that the position of the Dirac node is shifted. And this, from this you can see that indeed the phonon field works as an effective gauge field. In addition to shift of the Dirac node, actually you can see also that there's a deformation of the Dirac cone. And I will show later that actually this can be also regarded as a effective gravity acting on the Dirac fermion. Okay, so now I have already told you that the phonon can be regarded as a gauge field. So how does this gauge field can give rise to a large phonon magnetic moment? And here let's say we use a low energy theory. For example, if we only consider the physics near Dirac cone, and this is the effect Hamiltonian described in electron coupled to the optical phonon field, right? And here I also introduce the physical electromagnetic field. So big A is the real electromagnetic field, and the small a is the emergent gauge field due to phonon. Okay, and because the phonon field is time reversal even, so between values, so it must change sign. So here this tau is the value index. So it's a +1 for the k value and -1 for the minus k value. Now let's consider what happens if we apply magnetic field. Because when we measure the phonon magnetic moment, we need a magnetic field to split the left hand and the right hand phonon. So with magnetic field, there will be a Hall conductivity, right? And this Hall conductivity can be described using the so-called Chern-Simons term given by this expression. And so if you take derivative, you get the Hall response due to the external electromagnetic field. And for this Chern-Simons term, it's second order in big A, the physical electromagnetic field. So this means that if we translate into emergent gauge field, it's also second order, then the value index drop out, right? So we got effective action for the emergent gauge field or for the phonon field. That is the same form as the standard Chern-Simons term. And here we have consider the time reversal symmetry breaking system. That's why we have Chern-Simons term diagonal in the big A or in small a. But if we have time reversal symmetry, actually we can have a cross response, basically the response between big A and small a, and this was discussed in our recent publication. Now here, because of Chern-Simons term, actually it can give the phonon Hall viscosity, which is non-dissipative. So remember that for the emergent gauge field, it's related to the phonon field in this way. So for the x component of the emergent gauge field, it's related to the uy. That's the optical phonon field. And if we substitute, in terms of the optical field, we get the Phonons viscosity. Okay, so this is the Lagrange for the Phonons viscosity, which is non-dissipative. Basically, the phonon have also experience an effective magnetic field that is proportional to eta, and eta is also is basically the Hall conductivity. So in that way, we establish the connection between the phonon Hall effect and also the electrical Hall conductivity. And for the optical phonon, we have a standard Hamiltonian describing the left-hand and right-hand optical phonon. And if we solve this Lagrange, you can get the phonon mode or the phonon frequency. And for the left hand and for the right hand, there will be splitting due to this phonon Hall viscosity term. Okay, this eta is the splitting of the phonon magnetic moment. And this is a plot. So if we apply magnetic field, so you see there will be a splitting of between left hand and right hand phonon. And from this splitting for small field region, we can extract phonon magnetic moment. And in this case, it's about it's a lot of electron ball magneton, depending on the parameters. And I also want to mention that actually in the graphene system, there's some preliminary results which already show that there's a huge phonon magnetic moment. And this is a magneto-Raman scattering of graphene. And you can see there's a splitting of the phonon mode and the Tesla magnetic field. From this splitting, actually, one can roughly estimate the moment of the phonon, which is roughly about 2 μb, which is considered with our theoretical explanation. Okay, now let's move to the experimental system that is cadmium arsenic. This is also a prototypical 3D Dirac metal. We have two Diracons along the KZ direction. So here's one Diracon, and there will be another Diracon at the time reversal point. And we also did a DF calculation, and we found that indeed there are several phonon mode at the gamma point. For example, we have a EU mode, which is odd under spatial inversion, and also have EG phonon mode, which is even under the spatial inversion. Now let's first look how this phonon mode coupled to the Dirac fermion. As I mentioned, in order for the phonon field to be regarded as a gauge field, it must be compatible with the symmetry, the little group at the Dirac point, right? Okay, so let's say if we want to have a gauge field description, so we should have this form, right? And we also have two Diracons, so there will be a really by time reversal. So there are two values as well. So we have a plus and minus. Okay, just have two values. And for the EG phonon is even under spatial inversion. And for this phonon mode, actually, it is compatible with this symmetry requirement. So it can be regarded as a gauge field. However, for the EU phonon, which is odd under spatial immersion, actually this is not compatible with symmetry requirement. So for the EU phonon, it cannot be regarded as a gauge field. And we can also do the same basically calculation based on Tadamai model using those low energy orbitals, and you can derive exactly this form of electron phonon coupling from the Tadamai model, as I showed you before for the graphene system as well. And indeed, the emerging gauge field is related to the to this phonon field, and it's basically the EG phonon field, which are two indices, and it's even under spatial inversion. And to verify this picture explicitly, we also did a DFT calculation. So this is first, let's say we don't have any phonon field, then the Dirac point is sitting at this point. Now, if we excite the EG phonon, and you can see that the position of the Dirac node is shifted a little bit, and at the same time, it's also got deformed, similar to the case of graphene. So this is considered with the shift of the node is considered with the description based on the gauge field. And because this electron phonon coupling in terms of gauge field, and we also expect similarly there will be a phonon Hall viscosity term, and in that way we can produce a large phonon magnetic moment. And indeed we did some estimate using the material relevant parameters, and what we get is that the phonon magnetic moment is of order of 1 electron volt magneton. And this phonon field also have other consequences, such as the so-called Chiral anomaly, because this basically phonon is work as some effective magnetic field or electric field, which can produce similarly the Chiral anomaly due to the physical electromagnetic field. And this has been discussed in this paper some time ago. Now let's consider the other phonon mode, the EU phonon mode, which is odd under spatial inversion. And in this case, as I mentioned, this cannot be regarded as gauge field because it's not compatible with the little group at the key point. And this is the DFT calculation. So indeed, you can see that if we excite this phonon field, the position of the node doesn't change, right? So there's no shift over the Dirac node, which means that this is not a gauge field. However, you can see there's a deformation of the Dirac node. So now the question is how to describe this phonon field, because that's what I said before. And here I will show that actually in this case we should regard the EU phonon as some effective gravity, and this can be described in terms of the frame field. That is also a tensor which changes basically the metric of the space. So for this, in the presence of this phonon field, so the Dirac equation gets modified. So here is a modified Dirac equation because of the frame field here, right? So without this system, we have standard Dirac. We have a Dirac formula moving in the flat space, but because of the frame field, it moves in the curved space. Okay, and because of this frame field, it modifies the dispersion of the Dirac formula, and as shown in this DFT calculation. We can do the same operation by integrating out the electrons, and we can get this effective action for the frame field, and that's given by this expression, and the coefficient is basically is a metric of the space. So if we in the present magnetic field, we have lambda levels, and if we fill those lambda levels, we can get the Hall viscosity, and which is proportional to the filling fraction. And also for the Hall conductivity, it's also proportional to the filling fraction. Basically, we have two quantities. One is the Hall viscosity, eta h, and also another is the Hall conductivity, and they are proportional to each other. Okay. And if we, we can also, do the calculation and relate the EU phonon field to the frame field. Actually, for the in the case of cadmium arsenic, and we have this simulation. This is the EU phonon field Ux and Uy, and this is frame field, as they are proportional to each other. And if we substitute, the phonon field into the effective action for the frame field, again we get the Hall viscosity term for the phonon. Again, it's an effective magnetic field for phonon, and because this is effective magnetic field, we get a splitting of the left-hand phonon and the right-hand phonon. And from the splitting, we can estimate the phonon magnetic moment, which again is proportional to the electrical Hall viscosity times the electron phonon coupling squared. And this is our DFT calculation. So this is a plot of the phonon frequency splitting as function of magnetic field. Again, from this plot, we can estimate the phonon magnetic moment, and this gives us the same order of magnitude observed in experiment. Okay, this is a summary slide. So here I showed you there are two kind of phonon field depending on symmetry. One is the EG phonon, which is even under spatial inversion, and also EU phonon, which is odd under spatial inversion. For these two phonon field, depending on the angular momentum. So for for the inversion even phonon or for the EG phonon, it can be regarded as a gauge field, as I showed before. So gauge field means we have a displacement of the Dirac cone, and this corresponds to the angular momentum equal to 1 deformation of the Dirac cone. And at the same time, there are also some deformation of the Dirac cone, and this corresponds to the different angular momentum channels, such as L equals 0, which is the breathing of the Fermi surface of the Dirac cone, or L equals 2, that's like a nematic deformation of the Dirac cone. While for the EU phonon, it cannot be regarded as a gauge field, so there are no L equal to 1 channel deformation. It can only happen in the even channel, like L equal to 0. It's like breathing of the Dirac cone or the nematic deformation of the Dirac cone. And for the phonon magnetic moment, for the EU phonon, it's proportional to the Hall viscosity, electrical Hall viscosity, and for the EG phonon, it is proportional to the electric Hall conductivity. This is a summary slide. This is basically what I have just described. And because in our problem we can produce a large phonon Hall viscosity term, so this also implies there will be a large phonon thermal Hall conductivity. And here also I would like to highlight, since the phonon field can be regarded as a gauge field or can be regarded as a gravity. Actually, the materials, the Dirac metal with phonon field, actually mimic the baby standard model. Right? So we have a small universe in this material, which is it's very, I think, nice theoretically. And so this is our two work related to this presentation. And if you're interested, you can look at those two papers for more details. So let's end here, and I will thank you for your kind attention. I'm happy to answer any questions.